Hello and welcome to Angles, Scale and Coordinates with me, Bill Henning. Now the objective of today's session is to use angles when describing position and direction and measure angles in degrees, calculate values of angles and or coordinates with 2D and 3D shapes, recognize and make use of simple scales on maps and drawings, calculate actual dimensions from scale drawings and create scale diagrams giving actual measurements. Use coordinates in 2D, positive and negatives, to specify positions of points and any other areas that may come up. Now let's look at angles. All right, now all angles must add up to 360 because in angles 360 is the magic number. Now let me just expand on that. Now a full circle is 360 degrees. Okay, so you may remember from your perimeter area and volume, that's the circumference or the perimeter. Okay, now the distance around there is 360 degrees, which is the magic number. Now a semicircle or a straight angle is half a circle. So therefore, half of 360 is 180, and this is called a straight angle. Okay, the distance from there to there is a straight angle. It's an angle that's often forgotten in maths. Now the right angle is a quarter of a circle. And you can see the distance from there to there must be a quarter of the magic number, which is 90 degrees. Okay, and other angles, these are other angles that may pop up, so you have to be aware of what they are. So you can see the acute angle is anything between 0 and 90. Then you have the obtuse. You may remember these two from school days. So the obtuse goes from 90 to 180. And this one here, in this area here, is called the reflex. This is the one that most people forget, is a reflex. So the reflex goes from 180 up to 360. So that's your basic angles within a circle. Now let's look at four-sided shapes. And again, you'll see why 360 is a magic number. Okay, all the angles in a four-sided shape must add up to the magic number of 360 degrees. So you can see there in this example, you have a right angle, which is 90 degrees. 4 times 90 is 360. Now you also have to remember that opposite angles are the same size. All right, so you can see that opposite angle there is going to be a right angle as well. Okay, so remember that applies to all shapes. Opposite angles are the same size. All right, and there's your different types of shapes, four-sided shapes. All the angles in here must add up to 360, which is a magic number. Now let's look at triangles. Now all triangles are half a square or half a rectangle. Therefore all the angles in a triangle must add up to 180 degrees, which is half the magic number. And if you look at these examples, if you remember from some of the other videos you may have seen, we've talked about a line of symmetry. So if you draw a line down the middle there, you can see both of these are a mirror image. And if you remove that, you can see why a triangle is half a square or half a rectangle. And it's similar with this shape here. You can see that the area of this shape here is the same as these two added together. So therefore all triangles are half a square or half a rectangle. And therefore all the angles must add up to 180. So let's explore triangles a little bit further. You can see an equilateral triangle. All the sides in an equilateral triangle are the same size, so therefore all the angles in an equilateral triangle must be 60 degrees because they must add up to 180, so that's 60, 60, 60. Let's look at the old isosceles triangle. Okay, again, you can see here with this one, you've got these little scores going through these little dashes. What that means is that both these lengths are the same size. Now if both these lengths are the same size, then both these angles must be the same size at the bottom. Okay, so you may get a question to just gives you that angle there. Well, you can just deduct that from 180, divide it by 2, and it will tell you what these are. So the lines on the triangle mean that both sides are the same length, therefore the angles at the bottom are both the same. Okay, now you have a go. Calculate the size of angle X. Pause the video and see how you got on. So how did you do? Let's have a look. Now you calculate the opposite angle 80 degrees. So you can see now that that angle must be 80 degrees. Knowing this, you add both the angles, then deduct it from the magic number. Okay, and you can see that leaves 200 degrees. Now we know the opposite angles are the same, so we just divide this 200 by 2 to find angle x. And you can see that angle x is 100 degrees. So if you got 100 degrees, fantastic, well done. Now let's see if you remember your angles. What type of angle is shown? Again, pause the video, see how you do. Think about it. So which one did you choose? Well, if you choose obtuse, then fantastic, because remember, obtuse goes between 90 and 100 degrees. So well done. Now, measuring angles. To measure angles between the lines, you can use a protractor. Okay. Now, the first step is to center the protractor with the fixed point where the lines meet, which is this part here. So you line up the center, you can see, as you line it up. Then what you do is you line the bottom line of the protractor with one of the lines. So you're lining up with this line here. And now you can read off the protractor. We can see if this is acute angle is 55. Now with protractors you can read from left to right or right to left. You can see how they're calibrated. Okay. Now if you want to work out the obtuse angle, you can start from the outside zero here, work your way around, and you can see that it comes to 125. But if you work backwards, you start from zero here and you work your way to the left using the inner circle. Okay, you can see that that angle is 55. So that's how you measure angles using a protractor. Now bearings. Bearings denote the direction of one point to another, given its angles in degrees. They are always measured clockwise. You never go anti-clockwise when you're doing with bearings, and you always start from north and work in a clockwise manner. And are written in 3 digits. For example, the angle 42 degrees is then written as 042 degrees. Okay, so the example here is the bearing to B from A is 127, and you can see the angle from A to B is 127. All right, so if you get your protractor out, that's what it is. All right, therefore A to B is on a bearing of 127 on a heading in a southeasterly direction. Now you remember that's north, okay, and east is that direction. Okay, so you're heading in a southeasterly direction. Okay, so now you have a go. Right, a boat is sailing north. It turns 100 degrees in an anti-clockwise direction. Which one of the following shows the direction in which the boat is now sailing? Pause the video, have a go. How did you do? Well, if you got the answer B, well done. Now, in what direction is the boat now heading? Again, pause the video, think about it. How did you do? Well, you can see the boat is now heading southwest. Okay, so south is in that direction, west is in that direction, so he's sailing somewhere in between. So he's heading in a direction of southwest. And if you got southwest, well done. Now let's move on to scale. Now scale is a crucial component of maps and scale drawings. It represents the relationship between the measurement on a map and the actual measurements in real life. Now scale factors are used to accurately scale up or scale down an image. Scale drawings come with a key or a scale factor that indicate what dimensions in the drawing are equal to in real life. Okay, scale factors are usually represented as ratios. So here's our old friend ratios again, with an equal sign or as a line drawing as seen on a 1 centimeter grid. Now, in functional skills, maps and scales are important concepts that help individuals understand and interpret the position, area, and size of things. Okay, so maps are visual representations of an area, typical of showing geographical features, cities, roads, and landmarks. Okay, they provide a scaled down version of a larger area, allowing individuals to navigate and understand the layout of the land. And maps can be used for various purposes such as navigation, planning, and understanding the distribution of resources. So let's have a look at this table. Now each one of these little squares on that grid there represents 1 centimeters, and you can see now how scale can be written. It can be written in a few forms. Okay. Now the one on the left hand side here of this part of the ratio in here and here, that will always be 1 centimeter. These squares are always 1 centimeter on your plan or on an exam monitor or whatever it is. They will represent 1 centimeter. A lot of people don't realize that. And what the number on the right hand side, that represents real life. So for example, if that was 1 centimeter on a plan, that represents 100 meter in real life. If it was 1 centimeter on the plan, it could represent 10,000 centimeters. Now you'll notice in the first one it mentions meters there, right? But in real, when you get a situation like this where it doesn't mention the denomination, then it's centimeters. All right, so that's 1 centimeter represents 10,000 centimeters in real life. Okay, just remember that. No denomination, then it's centimeters. And you can see this one just gives you little arrows to tell you that that 1 centimeter represents 100 meters. And that's a distance mark represented there. Now, if you look at these three different ways of presenting scale, you will notice that they all mean the same thing. All right, so be careful when you're reading them. Scale drawing. Now the scale drawing below shows a section of coastline. Calculate the distance between point A and B as the crow flies. Okay? When scaling up to real life, we multiply by the key value. What is the key value? Well, there's the key value there. The key value tells you that for 1 centimeter, it's the same as 5 kilometers in real life. Okay, so all you simply do is you measure it using a ruler, and you can see the distance on the plan or the map is 8.5 centimeters. We then just simply multiply that by the key value, which is 5. All right, and you can see there 8.5 times 5 is 42.5 kilometers. So when you're going from the plan to real life, you multiply by the key value. Scaling down from real life, we work in reverse by dividing by the key value. Okay, so let's have a look at that key value there. Now, if the distance between A and B is 42.5 kilometers, what is this represented on the map? And again, all you simply do is you take this value and you divide it by the key value to shrink it down to the size you want. And you can see 42.5 divided by 5 gives you 8.5 centimeters. So you can see there by reversing it, you get back to your 8.5 again. So the key to this is the key value. We're presenting it. Below is a map of Africa. Calculate the real life distance between Dakar and Khartoum, marked on the map. Okay, so all you simply do is you count the 1 centimeter squares between the two cities, and you can see there's 1, 2, 3, 4, 5.5, 5.5. Okay, and again you take that 5.5 and you multiply it by the key value, and in this case the key value is 500. Okay, so you take 500, multiply it by 5.5, and that tells you the distance between Dakar and Khartoum is 2,750 miles. Could be simpler. Here is a level 2 question that needs careful thought. Okay, now that we know that's what scale means and how it's presented, we have to remember about things like different denominations and how they present it. So in here, an estate agent needs to know the area of a plot of building land. This plan shows the building land, and it says there, what is the area in square meters? Now this is a very, very tough question. So you have to break it down and understand how scale works. Okay, so the first thing you have to do is you can see this scale is in centimeters because it doesn't give you the denomination. So what you have to do is take these millimeters and convert them to centimeters. So you see there, you now convert the millimeters to centimeters to match the key. And you can, if you remember your converting metrics session, you use a little table to convert millimeters to centimeters by dividing by 10. So you can see there that 16 millimeters is the same as 1.6 centimeters, and 66 millimeters is the same as 6.6 centimeters. Right, so you then multiply both by the key value. All right, and you can see there, right, that it's 1.6 times the key value is 2,000 centimeters, and the one down there is 8,250 centimeters. Now the next thing is you have to convert these to meters because they're asking you the area in meters. All right, so what you do is you just divide them by 100, and that converts centimeters to meters. So you can see here you're using the full range of your conversion grid to get to this answer. You're going from millimeters to centimeters and centimeters to meters. And now you're in a position where you can work out the area in meters. So you multiply to find the area, and you can see that 20 multiplied by 82.5 gives you 1,650 meters squared. Don't forget your little 2 because you're working in 2 dimension. So you can see at level 2 the question can be quite difficult, but as long as you know your basic processes and understand what scale means, then you should be able to tackle that type of question. Typical level 2 question. Okay, now a gardener wants to build this greenhouse in the top right hand corner of her garden. Okay, she will leave a 50 centimeter space between the greenhouse and the edge of the garden. Okay, she wants a scaled plan of the garden showing the position of the greenhouse, and it says draw a scale plan. Okay, so the first thing we have to do is put the scale you use on the plan. Okay, so you can see there you've got your size there, and you can see that one of these little squares, the 1 centimeter squares, represents half a centimeter based on these calculations here. But you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of these little squares. So if you take 11 and divide it by 0.5, you'll get 5.5. Okay, so you do your calibration, or you could put 1 in 50 centimeters. And then from that, you can use these dimensions here to convert to either centimeters or use the top scale. So you would draw your plan based on that, and you can see there that 1, 2, 3, 4. So if that's 4 times 0.5, that must be 2 meters. And this one is 4.5. 4. That's 5 actually. So 5 times 0.5 is 2.5. Okay, and that's how you plan. And don't forget, it's 50 centimeters away from the edge. You just follow the instructions in the questions, and you must get it right. Okay, so now you try it. Part of a map is shown below indicating the location of 2 cities. Calculate the real-life distance between Townsville and Hobart. Pause the video and have a go. So how did you do? Very simple. The distance between Townsville and Hobart is 5 squares. 5 times the key value, you can see is 1,600 kilometers. And if you got that, well done. Try these questions. In a town, a church is situated 800 meters away from the train station. A map is drawn using the scale 1 to 250 meters. All right, so work out the distance between the church and the train station on the map. Pause the video, have a go. So how did you do? All right, so just take 800, divide it by the key value, 250, and that tells you that on the map the train station is 3.2 centimetres apart. Now on a map, Liverpool is 11.2 centimetres away from Manchester. The scale used to draw the map is 1 in 500,000. Now remember, that's in centimetres. Okay, work out the distance between Liverpool and Manchester in real life. Give your answer in kilometres. So you can see this is handy to know how to convert using the little conversion grid that you learnt from your converting metrics session. So make sure you understand how that works, and that way you won't get something like this wrong. Okay, so let's work through it. Pause the video. See if you get the answer. How did you do? Well, you can see the first thing you have to do is you multiply 11.2 by 500,000. Okay, and you can see that gives you 5,600,000 centimeters. You then have to divide that by 100 to convert to meters, which gives you 56,000 meters. Okay, and then you have to convert that to kilometers by dividing by 1,000, and you can see that the actual distance between Liverpool and Manchester is 56 kilometres. So if you got 56 kilometres, you're doing absolutely fantastic. So well done. Right, the diagram below is a scale drawing of a bus. The length of the bus in real life is 12 metres. A ruler is used to measure the length of the bus in the drawing, and you can see it's 6 centimetres. Now work out the scale used in the scale drawing. Give your answer as a ratio in its simplest form. Again, pause the video, see how you got on. So how did you do? Well, first and foremost, you create the ratio. 6 centimetres equals 12 metres in real life. And then you simplify it. Divide both numbers by 6. And you should come up with the ratio 1 to 2. And if you got the ratio 1 to 2, then well done. Now we'll have a look at coordinates. Now we use coordinates to describe positions of points on a grid in terms of their position along the x-axis, the horizontal, and the y-axis, the vertical. Okay, so there's your x-axis and there's your y. And if you ever forget what it is, then y, just think of that, the y-axis. Okay. Now, understanding coordinate grids. Now, points can be plotted and lines can be drawn on grids like that seen to the right. So that, like this grid here. Okay. Now, the grid is made up of two lines crossing called axes, meeting at the point in the middle called the origin. So there's your origin, and there's where the two lines cross. So there's your x-axis and your y-axis. Okay, the origin has the coordinates 0, well, open bracket, 0, 0, close brackets. All coordinates will have to be in brackets and separated by a comma, and you'll see why in a minute. Okay, so there's your 0, 0 to start off with. Okay, now coordinates are described by pairs of coordinates x, y, like for example in the brackets, separated by a comma, and represented by a dot or a cross. The x coordinate is always written first. All right, so the x-axis. Now when you're writing coordinates, remember this little phrase. You go along the corridor first from the origin before you get down the stairs. All right, you always start horizontal when you're putting in these coordinates. All right, we all have to sing from the same hymn sheet, so to speak. Okay, so you always go along the corridor, then up and down the stairs, depending on the number of values. Okay, keep that in mind. Of coordinates, you may be asked to find coordinates on a point on a grid. Okay, for example, what are the coordinates of the point A on the grid to the right? So you can see here, you've got this little dot here. It could be a cross, but you want to find, and this is coordinates A. Now the coordinate is the actual dot itself, not the letter A. So you're aiming to get here from the origin. So how do you do that? Well, it's relatively simple. You start at the origin, and you can see you move 2 spaces to the right, and then you move 3 spaces down, and that takes you to point A, or coordinate A. So you can see there that the coordinates for A is open brackets 2 and then -3 close bracket. Now that's because the two upper brackets are called the positive quarters and the two down below are negative. So positive numbers always go to the right and up. Negative numbers always go to the left or down. Okay, so that's the best way to remember it. So the coordinates for A are open bracket 2, -3. So then we can just go 2 -3, and that takes us directly to where that be. Right, plot the points 1, 3 on the grid. Again, it's the same as if you're plotting them. So you move right from the origin till you find 1 on the x-axis. So you move across till you find 1. Okay, then you move up from 1 until you're level with 3 on the axis and the y-axis. So you move up till you come to 3, and you can see there, you mark that position with a dot or a cross and label it 1, 3 within brackets. So there's your dot, 1.3. Okay, and that's how you plot on your grid. Now you can connect points on a grid to make lines or 2D shapes. Okay, for example, the grid on the right shows a triangle drawn by plotting 3 points and connecting them with straight lines. to give you the shape. Okay, we call this triangle ABC after the letters of its corners. So you can see there, ABC. It's as simple as that. Okay, you may be given dimensions in a questions, and you must use these to plot points to create 2D shapes. All right, so you might not be given a shape like that, but they'll give you coordinates, and this is quite common. You'll fill in the coordinates and then be asked to name the shape. Okay, that's quite common in maths. So let's look at this type of question. What are the coordinates of both points A and B on the map? Okay, fairly simple. A, you start from the origin and you move out from the origin till you get to in line with where the coordinate is. So it's 3 and 3 down. So again, remember, if you're going left, it's negative. If you go down, it's negative. So it's -3, -3, and that gives you the coordinate of A. And same with B, you start from the origin and you move right. Now remember, when you move right, it's a positive number, and when you move up one, it's a positive number. So you can see you go along 4 grids or 4 spaces in the grid and got 1, and you can see the coordinates are 4, 1. So that's how you plot or recognize grid references. Here's another example question. Points A and B have been plotted on the grid below. Given that ABCD is a square, what are the coordinates of C and D? Well, it's very simple. You can see that the distance from there to there is 4 squares, 4 of the squares grid, so it must be 4 across. So you just follow that through, and you can see 4 across gets you to C, and if you got 4, that will get you to D. Okay, and you can see there's the coordinates, 2, -1, and 2, 3. Okay, and then if you want to draw the shape, you just draw the shape, and you can see there's your perfect square. Let's look at map grid references. You can see the layout of this map. It's similar to your coordinate grid, okay, and the rules are just the exact same, but this time your origin is in the bottom left hand side, so you always go along the corridor first before you go up the stairs. All right, so let's look at the 2 types of grid references. Now we're going to look at a 4-figure grid reference. Okay, let's take 1753. What that means is 17 across, you break it into 2 parts, right? Just half it down the middle. So you go 17 across and 53 up. So you go across, you get to 17, and then you go up till you're level with 53. And what that does, it takes you to the bottom corner. It takes you to the bottom left-hand corner of the grid. And the location you're looking for will be somewhere within that grid. So somewhere within that grid is the location you're looking for. You have to look for it. Okay. And I know that's a flag, but it could be a ordnance survey map, okay, with a lot of different things within that area, and you have to go and search for what you're looking for. So that's a 4-figure grid reference. But what about the 6 grid reference? Well, the same rules apply, but what this does, it takes you directly to where you want to go. So you can take this 6-figure, and again you split it into 2, right? 195 and then 252. 195 you go along the corridor, okay? You can see that, and 195 just means 19.5 across. So you're stopping here, 19.5. All right, and then you go 52.5 up, 525. So you go up there till you get to 52.5, and you can see there that takes you directly to the treasure chest. Okay, so that takes you directly to where you want to go, whereas the 4 grid reference will take you to the bottom corner of the left hand side of that grid. And that is angles, scale and coordinates. So I hope that helps. Good luck.